I'm Anil Kumar, and in this video we'll estimate area under a parabola. The question here is, show that the area under the curve y equals to x squared from 0 to 1 approaches 1 over 3 using the approximating rectangles as number of rectangles approach infinitely large. So that's the question for you. So basically what we are going to do here is we'll actually approximate the area under the curve y equals to x squared, which is a parabola. So let me sketch one parabola here, right, like this. From 0 to 1, so let us say that this is 0 for us, and let me keep 1 slightly away. So let's say this is the upper boundary, 1 for us. Okay, so this is 1 for us. 1 square will be 1, so that value will also be 1. Now we need to find the area under this curve, rather show that this area is 1 over 3. That is the idea. And we have to use rectangles, some of the rectangles, to find this area. So in this particular case, we want to use infinitely large number of rectangles. Let us say n is the number of rectangles, right? When I'm saying n is the number of rectangles, basically I mean that this space is divided into n rectangles. So if I divide 0 to 1 in n rectangles, in that case, the width of each rectangle will be how much? We call this as delta x. That will be 1 minus 0 divided by n. So the width will be 1 over n, right? So what I'm trying to say here is that let's say this is my first rectangle, right? So I'm just making bigger so that we can see clearly. In that case, from 0 to 1 over n, that is the width of my rectangle. The next rectangle will be again 1 over n away, so it'll be kind of here, right? So that'll be 2 over n, right? So at 2 over n, I will have another rectangle, correct? Similarly, many will be there. So this is the second at 2 over n. So generally, we can say ith rectangle will be right there, right? Right there. So we'll call this as I over n, right? At I over n, we'll have ith rectangle, and the last nth rectangle will be at n over n, which is 1. Do you see that? So like this, we'll have number of rectangles. So to find the general formula, I will actually consider the area for the rectangle in general, which we are treating as I over n, and we'll sum it over from the first to the nth one, correct? We'll also use in our calculation the right corner to find the height of the rectangle, right? So for the height, you could use left, center. We'll use the right, right? The height will see the right corner, right? So if I'm using the right corner, in that case, you will see that our estimate will be slightly higher, right? So because, see, for example, if I form this rectangle, so that much is the extra, right? So we begin with the very first one, kind of like this, and we can continue like this. The last one will be kind of here like this. Is it okay? So that becomes the nth. This is ith. Okay. So we have n rectangles here. Sum of areas of these n rectangles will give us an estimate of area under this graph of y equals to x squared and the x-axis. That's the whole idea, right? We have to show that if n is very large, then this area is 1 over 3. That's the question. I hope the question is absolutely clear, right? You can actually pause the video and answer the question and then look into my suggestions. So let's find the sum of all these areas of the rectangles. So we say area will be equals to sum of all the rectangles. We are considering the general rectangle. Here, what is the width? Width delta x is 1 over n, right? So we'll say delta x is the width times height. So height is the value of the function at this point, right? Which is I over n. Is it okay? So ith one will be at x value of I over n. Now what we know here is that since we have taken n, we have divided the space in n equal parts, delta x is equals to 1 over n. So we'll replace that by this value. So we can write this as, and remember these rectangles, how many we have? From 1 to n. So I'll write I varies from 1 to n, right? So that is a summation, short way of writing the same thing, right? Okay, and that could be now written as sum of n rectangles, I equals to 1 to n. Delta x is 1 over n, so I'm writing 1 over n here. And what is the value of function at I over n? We'll replace x with I over n, so that gives us I over n whole square, right? Since the function is y equals to x squared. So this is the function. So we replace it with that value, right? I over n squared. Now, what we can write this as, we can write this as sigma I equals to 1 to n, 1 over n times I square over n square. Now I varies from 1 to n. These are numbers which are constant. So we could write this as 1 over n cube sigma I equals to 1 to n I square. Is it okay? Sum of natural numbers square, that is what we are getting. So basically, as you see here, we have 1 over n cube, and this sum is kind of a series, right? When I is 1, it is 1 square, plus I is 2, it is 2 square, I is 3, it is 3 square, plus so on till the last term, which is n square. So that is what we get. Now, I hope you remember the formula for this series of sum of squares. So we have done it in other videos. Let me just take this formula, which is a standard formula for sum of squares. We are not really deriving it here. We'll just substitute the formula. Formula is n times n plus 1 times 2n plus 1 divided by 6. That is the formula for this term. So what we've done here is we have replaced the series with that formula. Correct? So this is a very standard formula. Okay. Now we can simplify this a bit. 1n cancels, right? So what we have here is n plus 1 times 2n plus 1 divided by 6n square. Now the idea is that n has to be large so that we can find some accurate value for the graph. So we say when the rectangles, number of rectangles approach infinitely large, right? So if n is a large number, in that case what happens to this area? This is what we'll analyze now. So what we have here is a. Technically we can write limit n approaches infinity, right? Infinitely large number, and that is the expression we have, n plus 1 times 2n plus 1, and it is 1 over 6 here. So we'll write, let me write 1 over 6 outside, n square. So I'm writing 1n here and 1n with this. So it is 6n square. Perfectly same expression, but with a slight difference. See how it makes huge difference. It helps us to find this limit. 1 over 6 is a constant, so I'll bring it outside. And we are still working with the limit n approaches infinity. Now here, if I divide by n, what do I get in this bracket? 1 plus 1 over n. I get 1 plus 1 over n times, here we get 2 plus 1 over n. I get 2 plus 1 over n. Is it okay? Perfectly fine. If n is very large, what will happen to 1 over n? 1 divided by a large number approaches 0. So this will be 0. So basically we'll get 1 over 6 times 1 plus 0 times 2 plus 0, right? And that gives you, when you open this up, 1 times 2. So it is 1 over 6 times 2. And that is equals to, when you simplify, 1 over 3. Perfect. So this is what you get. So the area is 1 over 3. Do you get it? So that's the area which we could find by using limits. So when we use limits for n approaches infinity, you can see that we get fairly accurate result of finding area under any curved surface, right? So that is a very, very important exercise. I hope you appreciate it. You can always share and subscribe my videos and put some likes if you like. Thank you and all the best.